Hello everyone, we are from Group 2F. For OEL Hydraulics, we conducted an investigation of velocity profiles in an open channel flume under varying boundary roughness condition. So this is our group members, which is Adel Haris, Daniel, Umu, Amina and Nabil.
First of all, for the introduction part, there is a background of the velocity distribution. Free surface boundary is an open channel flow is exposed to atmospheric pressure, causing a non-uniform velocity distribution across the cross-section. Next, for the boundary layer growth is a frictional resistance along the channel bed and walls, retards fluid velocity, creating a developing boundary layer. Velocity maxima due to the boundary shear stress, fluid velocity is the lowest at the bed and the approaches is maximum closer to the free surface. Boundary sensitivity is a velocity profile are highly sensitive to changing flow regimes and the bed composition, which is a smooth, gravel and vegetation. Next, for the problem statement part, first problem is a theoretical limitation, which is a classic models like the logarithm law of the wall of fall short when predicting highly non-uniform real-world boundaries. Second problem is a need for empirical testing. Accurately mapping real-world boundary layer growth and displacement requires high-resolution spatial testing. And the last problem statement is a core challenge, which is quantifying the exact degree of the velocity retardation and the cross-sectional profile distortion caused by a varying boundary materials under the both low flow and the high flow regimes. Next, we move to the project objective. The primary objective of the experimental study are, first, to analyze the velocity distribution within a 4-meter multi-purpose teaching film under steady flow condition. Second, to quantify the distinctive structural effect of the low flow versus the high flow regime on the shape, uniformity, and the acceleration characteristic of the velocity profile. Lastly, to evaluate and compare the hydrodynamic impact of the three distinct boundary roughness type, which are standard smooth fume plate, uniform gravel, macro roughness, and a simulated plan on the boundary layer development and localized velocity retardation.
Now I will explain the materials and fluid used in this experiment. For all test configurations, we use water at ambient or room temperature. Using the same fluid throughout the experiment ensured that any differences in the results were caused by the channel bed conditions rather than changes in the fluid properties. To investigate how different boundary roughness affects flow behavior, we tested 3 channel bed configurations, which is the first configuration was the smooth bed, which consisted of a bare acrylic flume. This provides minimal resistance to the flow and serves as our baseline or reference condition. The second configuration was the gravel bed, where the channel was completely lined with the gravel. This represented a rough natural river bed and increased the flow resistance and turbulence. The third one is the vegetation bed, which used either the flexible or rigid artificial vegetations along the channel bed. This setup simulated vegetated river channel, which allow us to observe how plants influence the water flow and velocity distribution. By comparing these 3 bed conditions under the same flow rates, we were able to evaluate the effect of boundary roughness on hydraulic characteristics. Next, this slide presents the experimental apparatus and instruments used in the study. The experiment was conducted using a tilting flume, which allowed us to maintain control channel slope throughout the test. First, the flume was equipped with a recirculating pump system. This system supplied water continuously while allowing us to adjust and measure the discharge or flow rate in liters per second. Next, we used a point depth gauge to accurately measure the water depth at selected locations. Measurements were only taken after the flow becomes steady so that the data will be reliable. Next, to measure water velocity, we used a digital current meter which recorded point velocities at different depths within the water column. For every boundary roughness condition, velocity readings were collected at 2 locations, which is the first one called V1 was before the roughness transition, while the second one, V2, was after the transition. This setup allows us to compare how the roughness changes the flow velocities, flow characteristics as the water moves through the channel. Next, this slide summarizes the experimental procedure, which consisted of three main phases, which is in phase 1, we first adjusted and fixed the flume to a constant slope. Then for each bed conditions, we tested two flow conditions, which is the low flow condition was set to approximately 1 liter per second, while the high flow condition ranged from 1.4 to 1.8 liters per second. In phase 2, we measured the flow depth using the point depth gauge. These measurements were taken only after the water reached a stable, steady state condition to improve the accuracy of the results. Finally, in phase 3, we measured the vertical velocity profile. Instead of collecting data throughout the entire water column, we focused on three standard relative depth, which is 0.3 y representing the lower region near the channel bed, 0.5 y representing the middle of the flow, and 0.8 y representing the upper region near the water surface. This entire procedure was repeated for all three bed configurations and under both flow conditions, resulting in 6 experimental scenarios. So we repeat the same procedure for each scenario so that the consistency is ensured, and it will allow us to make a reliable comparisons between the different boundaries.
Next, I will continue to present on the experimental results. So starting with the smooth bed results. Under both low flow and high flow conditions, we can observe that the velocity increases from 0.3 y to 0.8 y. So this indicates that the water flows more slowly near the channel bed because of friction and becomes faster closer to the free surface. So we also found that the average velocity increased from about 0.31 meter per second during low flow to about 0.46 millimeter per second during high flow, showing that a higher discharge produces a higher flow velocity. So since the bed surface is smooth, there is very little resistance, resulting in a uniform velocity distribution. So next one is the vegetation bed. So compared to the smooth bed, the vegetation introduces additional resistance to the flow. Because of this, the flow pattern becomes less uniform, especially near the vegetation where the water experiences more drag. So as the flow changes from low flow to high flow, the velocity also increases. But however, the vegetation continues to slow the flow and increases the water depth due to the added resistance. Moving on to the gravel bed. Similar to the vegetation bed, the gravel surface creates additional roughness that increases friction between the water and the channel bed. And the velocity still increases from 0.3 y to 0.8 y, but the gravel causes energy loss, making the flow less uniform than the smooth bed. So under high flow conditions, the velocity is higher than the under low flow conditions, but the effect of the gravel roughness is still clearly observed. Moving on to the velocity profile graph. So this graph summarizes the velocity profile for all three bed conditions under both low flow and high flow conditions. So overall, we can see two clear trends. First is the velocity increases from the lower depth towards the water surface for all bed conditions. Second, higher discharge results in higher velocity. So the smooth bed shows the most uniform velocity profile because it has the least resistance, while the vegetation and gravel beds modify the flow due to their higher roughness.
Now we start with our discussions, starting with the analysis of our vertical velocity profiles, specifically focusing on the smooth bed baseline. As our dataset clearly indicates, boundary types and discharge rates strictly detect how velocity is distributed vertically in open channel. Looking at our smooth bed benchmarking, the bare acrylic flume bed exhibit highly stable, almost identical velocity distributions across both pressure stations V1 and V2. Under low conditions, the velocity remains tight and highly predictable, staying between 0.9 millimeter per second and 0.32 millimeter per second. When we step it up to high flow configurations, the flow accelerates uniformly, maintaining a stable range between 0.4 meter per second and 0.47 meter per second. The most critical hydrodynamic observations here is that the boundary layer growth is heavily restricted because the acrylic surface offers almost no frictions. Furthermore, we observe an absolute absence of the velocity dip phenomenon. This confirms to us that secondary current originating from the flume sidewalls are minimal and negligible under unobstructed conditions. Things become much more dynamic when we introduce macro roughness into the channel. Doing so creates significant spatial energy shifts and longitudinal non-uniformity. Let's look at the gravel bed first. Operating at a discharge of 1.0 liter per second, because the coarse interlocking gravel grains exert severe localized form drag. They create a dense boundary layers. This triggers a heavy upstream pulling effect at station V1, backing the water up to a depth of 0.42 meter and heavily retarding the flow velocity. However, to evaluate the volume of water, an acute local drawdown gradient is triggered at station V2. This rapidly converts that stored potential energy into a high kinetic state, causing the velocity to peak of 0.52 meter per second. In contrast, the vegetation spread at a higher discharge of 1.85 liter per second. The plant matrix introduces extensive drag, but because it is porous and flexibly spaced, water can pass through it. These structural arrangements distribute the drag differently, creating an even larger upstream backwater pool of 0.51 meter at stations V1 to store potential energy. As it passes through, the local drawdown shifts this head into a kinetic state, resulting in a more modest controlled peak velocity of 0.49 meter per second at station V. Then we move on to the quantifying the effect of laminar versus turbulent flow conditions. So the overall flow dynamic shift when moving from low flow to fully developed turbulent high flow conditions. Under low flow dynamics at 1.0 liter per second, the fluid possesses lower overall kinetic energy. Because of this, the velocity changes across our vertical depth points are minor but distinct. For instance, in our gravel V2 profile, we see a steeper velocity gradient near the bed, with velocity climbing progressively from 0.36 meter per second at the lower column to 0.42 meter per second at the surface. These steep gradients show us the localized viscous and form shear play a dominant role when initial force are limited. However, when we observe high flow dynamics between 1.4 and 1.85 liter per second, the increased discharge leads to fully developed turbulent conditions. Here, in here, intense turbulent emissions completely redistributes momentum evenly across the upper water columns. This results in a massive profile flattening effect, which you can see clearly at our accelerate V2 stations. For example, the vegetation high flow varies only slightly from 0.47 to 0.49 meter per second, and the gravel high flow is confined to a tight window of 0.49 to 0.52 meter per second. This uniformity proves that high turbulence successfully flattens the core velocity distributions. Flatten the core velocity distributions, effectively confining steep velocity drop to a very narrow regions right above the macro roughness boundaries. Here, we compare our three scenarios under high flow conditions. If we look at the smooth bed first, operating at 1.85 liter per second, it represents our baseline with the lowest mannings. Because the boundary shear is minimal, the water moves swiftly and uniformly at a shallow, stable depth of 0.9 meter across the channel. When we introduce our vegetation bed at the same discharge of 1.85 liter per second, we observe a moderate to high mannings. Although the plant matrix introduced extensive drag, its porous structural elements distribute this force. This creates an upstream backwater pull of 0.51 meter to generate adequate head, which then transitions into a modest kinetic surge of 0.49 meter per second as it clears the transition zone. Finally, the gravel bed represents our highly effective hydraulic resistance. Even when operating at a lower discharge rate of 1.4 liter per second, the coarse interlocking gravel grain boundaries exert severe near bed shear and localized from drag. This creates a dense boundary layer causing heavy upstream pulling at station V1 up to 0.42 meter. To evacuate this volume, a highly acute drawdown gradient is established, rapidly converting the stored potential head into our maximum recorded velocity of 0.52 meter per second at station V2. This clearly demonstrates that while micro roughness dramatically increase flow depth and local resistance, the spatial transitions trigger significant local acceleration state to maintain mass balance.
Finally, I will conclude our experiment and present a few recommendations. From this experiment, we successfully analyzed the velocity distribution in an open channel under different flow conditions and channel roughness. The result shows that the water velocity increased from the channel beds towards the free surface because the friction is lower near the surface. We also found that a higher discharge produced higher velocities and more turbulent flow. In terms of channel roughness, the smooth bed offered the least resistance, while the gravel and vegetation bed slowed down the flow. Among them, the vegetation bed had the greatest effect because it created the highest flow resistance. Overall, the experimental results agreed well with the hydraulic theories discussed in our report, including the effects of boundary friction, turbulence, and manning concept. Therefore, we can conclude that all the objectives of the experiment were successfully achieved. For future improvements, we recommend repeating the velocity measurements and using the average values to improve accuracy. The flow should also be allowed to reach steady state conditions before taking any readings. In addition, more measurement points can be added to obtain a more detailed velocity profile. Future studies can also investigate different channel slope, flow rates, and roughness material to better understand open channel flow behavior. Lastly, all measuring instruments should be properly calibrated and laboratory procedures should be followed carefully to minimize errors. That concludes our presentation. Thank you.